Disadvantages. Although many of the disadvantages are the subject of ongoing research, the current disadvantages of the Wankel engine in production are the following. Rotor sealing. This is still a minor problem as the engine housing has vastly different temperatures in each separate chamber section. The different expansion coefficients of the materials leads to imperfect sealing. Additionally, both sides of the seals are exposed to fuel, and the design does not allow for controlling the lubrication of the rotors accurately and precisely. Rotary engines tend to be over-lubricated at all engine speeds and loads, and have relatively high oil consumption and other problems resulting from excess oil in the combustion areas of the engine, such as carbon formation and excessive emissions from burning oil. By comparison, a piston engine has all functions of a cycle in the same chamber, giving a more stable temperature for piston rings to act against. Additionally, only one side of the piston in a 4-stroke piston engine is being exposed to fuel, allowing for oil to lubricate the cylinders from the other side. Piston engine components can also be designed to increase ring sealing and oil control as cylinder pressures and power levels increase. To overcome the problems in a Wankel engine of differences in temperatures between different regions of housing and side and intermediary plates, and the associated thermal dilatation inequities, a heat pipe has been used to transport heat from the hot to the cold parts of engine. The heat pipes effectively direct hot exhaust gas to the cooler parts of the engine, with resulting decreases in efficiency and performance. In small displacement, charge-cooled rotor, air-cooled housing Wankel engines, that has been shown to reduce the maximum engine temperature from 231 degrees Celsius to 129 degrees Celsius, and the maximum difference between hotter and colder regions of engine from 159 degrees Celsius to 18 degrees Celsius. Apex seal lifting. Centrifugal force pushes the apex seal onto the housing surface, forming a firm seal. Gaps can develop between the apex seal and trochoid housing in light load operation when imbalances in centrifugal force and gas pressure occur. At low engine RPM ranges, or under low load conditions, gas pressure in the combustion chamber can cause the seal to lift off the surface, resulting in combustion gas leaking into the next chamber. Mazda developed a solution, changing the shape of the trochoid housing, which meant that the seals remain flush to the housing. Using the Wankel engine at sustained higher revolutions helps eliminate apex seal liftoff, and makes it very viable in applications such as electricity generation. In motor vehicles, the engine will be suited to series hybrid applications. While currently being promoted as viable for electricity generation by those who see gensets as providing steady engine speeds and loads and the ability to precisely design the engine and match it to the application, Wankel engines are all but unknown in electrical generator sets of any size. While those applications appear to require steady speed and load, they in fact require rapid throttle response and accurate and precise engine controls to maintain the proper engine speed and generator output to meet changing demands when used for portable generator sets. They are also subject to increasingly strict emissions, fuel economy and noise standards and requirements, and are expected to run long periods of time with little or no maintenance and service apart from adding fuel. With their relatively high oil consumption and the need for large oil supplies or frequent checks of oil level and addition oil, Wankels would be at a huge disadvantage even if the emissions, noise and fuel efficiency requirements didn't handicap them. Wankels don't scale up or scale down nearly as well as piston engines, and their inherent flaws in design and operation make them very difficult to achieve acceptable fuel economy and emissions requirements with. Because they lack camshafts and valves and the timing of the engine is literally built into the rotor housing when the ports are designed and positioned and machined, they suffer the same problems and lack of tunability that two-stroke piston engines have, which result in those engines being equally hard to achieve fuel efficiency and emissions standards with. The camshaft of a four-stroke engine is literally its brain, and without a camshaft controlling both intake and exhaust event timing and duration, both Wankels and two-stroke engines are dumb, with Wankels being especially so. Slow combustion. Fuel combustion is slow, because the combustion chamber is long, thin, and moving. Flame travel occurs almost exclusively in the direction of rotor movement, adding to the quenching that is the main source of unburned hydrocarbons at high RPM. The trailing side of the combustion chamber naturally produces a squeeze stream that prevents the flame from reaching the chamber trailing edge. Fuel injection, in which fuel is injected towards the leading edge of the combustion chamber, can minimize the amount of unburned fuel in the exhaust. Where piston engines have an expanding combustion chamber for the burning fuel as it's oxidized and decreasing pressure as the piston travels toward the bottom of the cylinder during the power stroke is offset by additional leverage of the piston on the crankshaft during the first half of the travel. There is no additional leverage of a rotor on the crankshaft during combustion, and the crankshaft has no increased leverage to power the rotor through the intake, compression and exhaust phases of its cycle. Bad fuel economy. This is due to seal leakages, and the difficult shape of the combustion chamber, which results in poor combustion behavior and mean effective pressure at part load, low RPM. Meeting the emissions regulations requirements sometimes mandates a fuel-air ratio that is not conducive to good fuel economy. Acceleration and deceleration in average driving conditions also affect fuel economy. However, operating the engine at a constant speed and load eliminates excess fuel consumption. High emissions. As unburnt fuel is in the exhaust stream, emissions requirements are difficult to meet. This problem may be overcome by implementing direct fuel injection into the combustion chamber. The Freedom Motors rotor power Wankel engine, which is not yet in production, met the ultra-low California emissions standards. The Mazda Inesis engine, with both intake and exhaust side ports, suppressed the loss of unburned mix to exhaust formerly induced by port overlap. Although in 2 dimensions the seal system of a Wankel looks to be even simpler than that of a corresponding multi-cylinder piston engine, in 3 dimensions the opposite is true. As well as the rotor apex seals evident in the conceptual diagram, the rotor must also seal against the chamber ends. Piston rings in reciprocating engines are not perfect seals, each has a gap to allow for expansion. The sealing at the apexes of the Wankel rotor is less critical, because leakages between adjacent chambers on adjacent strokes of the cycle, rather than to the crankcase. Although sealing has improved over the years, the less than effective sealing of the Wankel, which is mostly due to lack of lubrication, remains factor reducing its efficiency. In a Wankel engine, the fuel-air mixture cannot be pre-stored because there are consecutive intake cycles. The engine has a 50% longer stroke duration than a reciprocating piston engine. The 4 Otto cycles last 1080 degrees for a Wankel engine, 3 revolutions of the output shaft, versus 720 degrees for a 4-stroke reciprocating engine, but the 4 strokes are still the same proportion of the total. There are various methods of calculating the engine displacement of a Wankel. The Japanese regulations for calculating displacements for engine ratings use the volume displacement of one rotor face only, and the auto industry commonly accepts this method as the standard for calculating the displacement of a rotary. When compared by specific output, however, the convention resulted in large imbalances in favor of the Wankel motor. An early revised approach was to rate the displacement of each rotor as 2 times the chamber. Wankel rotary engine and piston engine displacement, and corresponding power output can more accurately be compared by displacement per revolution of the eccentric shaft. A calculation of this form dictates that a 2-rotor Wankel displacing 654 cc per face will have a displacement of 1.3 liters per every rotation of the eccentric shaft, only 2 total faces, 1 face per rotor going through a full power stroke, and 2.6 liters after 2 revolutions, 4 total faces, 2 faces per rotor going through a full power stroke. The results are directly comparable to a 2.6-liter piston engine with an even number of cylinders in a conventional firing order, which will likewise displace 1.3 liters through its power stroke after 1 revolution of the crankshaft, and 2.6 liters through its power strokes after 2 revolutions of the crankshaft. A Wankel rotary engine is still a 4-stroke engine, and pumping losses from non-power strokes still apply, but the absence of throttling valves and a 50% longer stroke duration result in a significantly lower pumping loss compared to a 4-stroke reciprocating piston engine. Measuring a Wankel rotary engine in this way more accurately explains its specific output, because the volume of its air-fuel mixture put through a complete power stroke per revolution is directly responsible for torque, and thus the power produced. The trailing side of the rotary engine's combustion chamber develops a squeeze stream which pushes back the flame front. With the conventional 1 or 2 spark plug system and homogeneous mixture, this squeeze stream prevents the flame from propagating to the combustion chamber's trailing side in the mid and high engine speed ranges. Kawasaki dealt with that problem in its US patent US 3,848,574, and Toyota obtained a 7% economy improvement by placing a glow plug in the leading sight, and using reed valves in intake ducts. This poor combustion in the trailing side of chamber is one of the reasons why there is more carbon monoxide and unburnt hydrocarbons in a Wankel's exhaust stream. A side port exhaust, as is used in the Mazda Renesis, avoids one of the causes of this because the unburned mixture cannot escape. The Mazda 26B avoided this problem through the use of a 3-spark plug ignition system. At the 24 Hours of Le Mans endurance race in 1991, the 26B had significantly lower fuel consumption than the competing reciprocating piston engines. All competitors had the same amount of fuel available due to the Le Mans limited fuel quantity rule. A peripheral intake port gives the highest mean effective pressure, however, side intake porting produces a more steady idle, because it helps to prevent blowback of burned gases into the intake ducts which cause misfirings, caused by alternating cycles where the mixture ignites and fails to ignite. Peripheral porting, PP, gives the best mean effective pressure throughout the RPM range, but PP was linked also to worse idle stability and path load performance. Early work by Toyota led to the addition of a fresh air supply to the exhaust port, and proved also that a reed valve in the intake port or ducts improved the low RPM and partial load performance of Wankel engines, by preventing blowback of exhaust gas into the intake port and ducts, and reducing the misfire-inducing high EGR, at the cost of a small loss of power at top RPM. David W. Garside, the developer of the Norton rotary engine, who proposed that earlier opening of the intake port before top dead center, TDC, and longer intake ducts, improved low RPM torque and elasticity of Wankel engines. That is also described in Kenichi Yamamoto's books. Elasticity is also improved with a greater rotor eccentricity, analogous to a longer stroke in a reciprocating engine. Wankel engines operate better with a low-pressure exhaust system. Higher exhaust back pressure reduces mean effective pressure, more severely in peripheral intake port engines. The Mazda RX-8 Renesis engine improved performance by doubling the exhaust port area compared with earlier designs, and there has been specific study of the effect of intake and exhaust piping configuration on the performance of Wankel engines. All Mazda-made Wankel rotaries, including the Renesis found in the RX-8, burn a small quantity of oil by design, metered into the combustion chamber to preserve the apex seals. Owners must periodically add small amounts of oil, thereby increasing running costs. Some sources, such as Rotying.net, claim that better results come with the use of an oil in fuel mixture rather than an oil metering pump. Liquid-cooled engines require a mineral multi-grade oil for cold starts, and Wankel engines need a warm-up time before full load operation as reciprocating engines do. All engines exhibit oil loss, but the rotary engine is engineered with a sealed motor, unlike a piston engine that has a film of oil that splashes on the walls of the cylinder to lubricate them, hence an oil control ring. No oil loss engines have been developed, eliminating much of the oil lubrication problem.